Hi, this lesson is about the natural exponential function. With the natural exponential function, the base of an exponential function is going to be Euler's number, e. So before we talk about that, let's review what exponential functions look like. This is the family of exponential functions. There's several graphs here. The ones that are decreasing from left to right start up here in the upper left-hand corner of the second quadrant and then decrease. So these are the graphs of 1/2 to the x, 1/3 to the x, 1/5 to the x, and 1/10 to the x. So those are your exponential functions where your base is between 0 and 1. They decrease from left to right. The ones on the right, which start in the lower left-hand side of the second quadrant and then increase, are these: 10 to the x, 5 to the x, 3 to the x, and 2 to the x. The bigger the base, the sharper the increase. So this purple line here has a sharper increase than 2 to the x, which is the one in red. Notice that they all intersect at the same point, which is what we call the y-intercept, 0, 1, because when x is 0 in any of these functions listed above, the base raised to the 0 power will give you a y value of 1. So those attributes are here. The domain for all of the functions above are all real numbers. Your range are all positive numbers. That's why all of these graphs are in quadrants 1 and 2. There is nothing in quadrant 3 and 4. The y-intercept is 0, 1. Your horizontal asymptote is the line y equal to 0, which is the x-axis. When b is greater than 1, b to the x increases. That's all of these. And when b is between 0 and 1, b to the x decreases, which is all of these. So that's what was discussed in the last lesson. Remember that with these exponential functions, you can rewrite them in a different way by using your rules for exponents. So 1/2 to the x is the same as 2 to the negative x. And if you think back to chapter 2, the lessons that we did there, when the x changes sign, that's going to be a reflection across the y-axis. So 2 to the negative x is a reflection of 2 to the x. Those are the ones in red. So this one is a reflection of the other red one. And the same thing occurs with 1/3 to the x. It's a reflection of 3 to the x. 1/5 to the x is a reflection of 5 to the x. And 1/10 to the x is a reflection of 10 to the x. So what is e? So e will be the base when you are looking at the graph of a natural exponential function. And the definition of e is that e is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. But it really is just a number, and it's an irrational number, which is approximately equal to 2.71828. That goes on and on forever. That decimal goes on and on. So that's just an approximation. So that means that if e is about 2.71, then the graph of e to the x is going to look like the graphs where b is greater than 1. So in other words, the graph of b to the x is going to look more like these graphs where they're increasing from left to right. But all the other attributes will be the same. Domain is still going to be all real numbers. Range will be all positive numbers. X-axis will be your y-intercept, and x-axis is the horizontal asymptote, and your y-intercept will be at 0, 1. So here are some points. Again, you would need a calculator for this because e is irrational. So when x is -2, e to the -2 power is about 0.135. When x is -1, e to the -1 is about 0.368. When x is 0, e to the 0 is 1. Again, that is your y-intercept. When x is 1, e to the first power is about 2.718. When x is 2, e squared is about 7.389. When x is 3, e to the third is about 20.086. So if you were to plot these points, right, it is harder to plot decimals and fractions than it is integers, so you would approximate about what that is, but it would look a lot like the graphs that we graphed before of 1/2 to the x, 1/3 to the x, etc., in that your graph is increasing from left to right. So again, this is a summary of all of those attributes. We've stated them several times in the previous lesson and in this lesson. Really important that you memorize those and understand them and can apply them to what a graph would look like. So remember, if E is about 2.7 or so, then that means E is between 2 and 3. And that's exactly what it would look like on a graph. So 3 to the x is the one in blue, 2 to the x is the one in green. E to the x, which is about 2.7, that's closest to 3 to the x because 2.7 is closer to 3 than to 2, and that's the one that you see in red. And again, there's that point of intersection where they all meet, which is the y-intercept. All right, so in this next example, we're going to sketch the graph of negative e to the x. When you have a negative in front of the function, again, this is material that was covered back in chapter 2, that's going to be a reflection across the x-axis. So the graph e to the x looks like this, if this is 0, 1. And so e to the negative x means that you're going to flip e to the x across the x-axis. And so instead of having 0, 1 on your graph, you're going to have 0, -1 on your graph, and it will be decreasing from left to right. A lot of the same attributes will be the same. It'll still have a domain of all real numbers, but with negative e to the x, because it is reflected across the x-axis, here all of your y values are in the third and fourth quadrant, so your range is from -infinity to 0. There are no positive values of y. The graph is decreasing from left to right, so it's decreasing over all real numbers. It's got a y-intercept at 0, -1, but the horizontal asymptote is the same. It is approaching the x-axis, which means that I have a horizontal asymptote at the line y equal to 0. All right, so in this last example, we graphed e to the y equal to negative e to the x. And this next one, we're going to graph y equals e to the negative x. And this is the one where we're reflecting about the y-axis. Remember, e to the x would look like this. And so when I reflected about the y-axis, e to the negative x would be on the other side here, this one in blue. And so because this is the same as 1 over e to the x, and 1 over e is definitely a number between 0 and 1, so it's got that decreasing behavior instead of increasing behavior. And then again, a lot of the same attributes still apply. It still has a domain of all real numbers. The range for this graph here in blue is still all positive numbers. It is decreasing over all real numbers. It still has a y-intercept at 0, 1. And the the x-axis, or the line y equal to 0, is still the horizontal asymptote. It's getting close to the x-axis, but doesn't quite touch it. Okay, so in this next one, we're going to use a calculator to evaluate y equals to 0.5 e to the x plus 1 for values of x equal to -2 and pi. So you would need a calculator to evaluate this. Again, e is an irrational number, and so is pi. And that's going to be the second value that we plug in. So when x is -2, this is what you should be plugging into a calculator. It'll be 0.5 e to the -2 plus 1, and that gives you an approximate answer of 0.184 if you're rounding to the thousands place. Thousands place means 3 decimal places. And when you plug in pi and use pi, not 3.14, use the actual number, you should be plugging in this 0.5 times e to the pi plus 1. So the pi plus 1 is in parentheses because you have to add those numbers first and then raise e to that power. And that gives you an approximate answer of 31.451, again, when you round to the thousands place. Okay, this next one is also going back to a topic we talked about in chapter 2, which is a shift. Describe the shift of e to the x plus 2 from the parent function e to the x. State the horizontal asymptote and the y-intercept. So when you're adding 2 to the function, that's going to be a vertical shift up by 2 units. And if that shifts up by 2 units, that means your horizontal asymptote, which is usually y equal to 0. So for y equals just e to the x, the horizontal asymptote is y equal to 0. So when I shift up by 2 units, my new horizontal asymptote is y equal to 2. And to answer the question of x-intercept, you just plug in 0 where the x is. E to the 0 is 1. 1 plus 2 gives me an answer of 3. So 0, 3 is my y-intercept. So a graph of e to the x plus 2 looks like this one here below. The e to the x would go through here. So this would be the graph of e to the x, but e to the x plus 2 would be the one in purple. And so the one in purple has a domain of all real numbers. The range is from 2 to infinity. Remember, the whole thing shifted up by 2 units, so that means your range also shifts up by 2 units. And it doesn't include the 2, so I have parentheses around it. It increases from left to right. So it's increasing from -infinity to infinity. I have a horizontal asymptote at y equal to 2. That's the line in blue, the dotted line in blue, and a y-intercept at 0, 3. Okay, so here is a problem for you to try. Describe the transformation of y equal to -e to the x minus 3 from the parent function y equal to e to the x. Identify the domain, the range, the y-intercept, and the horizontal asymptote of this function here, and then sketch the graph. So give it a try. Good luck.